Let's talk about normalization. Normalization is, I can say, a way of creating the tables, and especially it is a systematic way. It has some set of rules, but why to follow them? If I don't follow normalization rules, if I create my own table, what are the problems I'm going to face? We will see first. Then you get motivation to learn normalization. So this is my table, watchman and area. So here I am going to collect all the watchmen along with the areas where they are, allotted. So every watchman is going to watch an area. So sometimes what happens, a watchman can watch multiple areas. These are all my requirements. So now let's introduce these attributes. Watchman ID is a unique identification number. So every watchman will have one unique identification number. So that's why let me make watchman ID not null. The reason is every watchman should be uniquely identified. If I write null value over watchman ID, then I can't differentiate two watchmens. Correct? Example, imagine you have two watchmens, both are null. Then how can you differentiate them? Example, you want to give salary to them. So it will be difficult, right? So it is easy to understand that every watchman should have a unique identification number which is not null. Similarly, every area, so here watchman ID is done, watchman name we write here and wife. Already I told you this is my table which is unnormalized. Then you might see some weird attributes. Okay, so let's allow that weird attributes without any reasoning. Example, every watchman's wife I am recording. Then here my assumption is watchmen are boys and every watchman has wife. Okay, that means married. Now I am writing here wife names. Now here area ID. So we are going to maintain the areas, right? That means every watchman is going to watch one area. Then that area's ID we write here, and every area will have some area name and area size. So this is especially these three columns, right side things are area information. Now this watchman ID, watchman name, wife represents watchman information. Now what I want to say is this area ID also not null, correct, because we cannot write null values here. If I write, then again I cannot uniquely identify one area. Now let's try to some insert some data into this. First of all, I take some watchman ID. At this moment, let's say this is a company, a big company which is providing watchmen to some areas. Okay, so government is going to give us areas where we provide watchmen. Now initially when you started this company, so there is no area allotted to you. So suddenly one day government called you and gave you some area. So that government said there is an area ID 1, area name let's say Gandhi Nagar GN, and area size is 1000 some square meters or something. So this area to be allotted for you, that means you have to provide watchmen for that. Then how do you do that? At this moment, let's say your company doesn't have any watchmen, then how you fill this data? You want to store every information in a table form. You don't want to remember them in your brain because it's a formal company. So that company has to remember this information. What is that? Government allocated you one area where you have to supply the watchmen. At this moment, let's say currently you don't have watchmen to allocate, then we have to write what? Null and null and null. This is the only way we can fill the data, correct? So if I do that, but already I have a constraint that watchman ID cannot be null. So here I can understand that to write area information, we need watchman information. At this moment, if there is no associated watchman, then we have to write null values, but we can't write because I want to say that watchman ID should not be not null and area ID should be not null. So here, so you are facing problem at watchman ID, correct? So to avoid this problem, you should change this constraint, but that's not good idea, right? So that's why I say that there is a problem. This is called insertion anomaly. That means while inserting some data, so you have to forcefully insert some other information which you don't have. So you face a problem that is called insertion anomaly. Now, to solve this insertion anomaly, what I do is I take one watchman ID 1, that means I recruit one watchman forcefully at this moment. Let's say that watchman is Raju and wife is, let's say, Rani. Fine. So somehow, so I mean acquired some watchmen. Now we'll see the data. Suddenly one more area came through government let's say that is 2, that is XYZ something, area size is 2000. Then to fill this data, again you have to write null values but not allowed. Then what to do? The same watchman I use, 1, Raju, Rani. See here. So you are repeating the information, remember it. So Raju's wife is Rani, of course, but in both places same information you are repeating unnecessarily because it is not a proper design. We know that, right? So we are slowly understanding the problems related to improper design. Now, suddenly, see this situation. There is one more employee, watchman, Rakesh came. Let's say Rakesh's wife is something Sita, and area ID, let's say 3 he is watching, and something ABC, and 3000 square meters. No problem, right? Now, if one more watchman comes, let's say 3, at this moment we recruited, one more watchman, but there is no area to allocate. That means he is not currently working for any area. Let's see this data. So let's say 3, Mr. Venu. So his wife is Swati. So random data I am taking. Currently we recruited watchmen, but we did not allocate any area because maybe he is in training period. He doesn't know how to watch the areas. Then what to do? So we say that this employee is on bench. Then at this moment nothing to watch. Then we have to write null values. Is it not again insertion anomaly? Because we can't write null value here because area ID not null. So here this area ID field is forcing us to write some value, but we don't have. That is called insertion anomaly. So finally you understand insertion anomaly. For that the only solution is one, immediately for this employee, otherwise watchman, we have to create one temporary area. Let's give same area 1 Gandhinagar 1000. So we say that Venu, you are not alerted, so you are temporarily allocated to this area. If you don't watch also no problem, Raju is already taking care of that. Only for our purpose, that means to fill some values here, I added these values. In that way we have to convince Venu. So that's why it's a problem, insertion anomaly. Now we'll talk about deletion problems. Example, let's say Rakesh want to leave the company. Then how what you do? Then you will be deleting this entire tuple. If you delete this entire tuple, then what happens? You lose area information 3, correct? So 3 is the area ID and area name ABC and area size 3000 square meters. You delete this data, right? So to avoid that, the only thing what we can do is, so here only part of the data we should delete and we have to write null, null, null. But the problem already watchman ID is not null. Then we cannot write null value here. Then this is problem, right? So while deleting, to delete some part of the data, this entire row we have to delete. If you do that, you lose your information. Second thing, you have to write null values, that is alternative solution. But if you do that, again your constraints may not allow you to delete this part of the data and write null values. So that's why I can say that this is deletion anomaly. You are facing problems while deleting the data. Now we'll see. So what is the solution then finally? What I do is I take a temporary employee like 3. Okay, from now onwards Venu is our temporary employee. So 3, Venu and Swati. Of course it's not a good decision, right? It's not a good solution. So you are unnecessarily keeping a watchman who is really not a watchman who is watching this area, correct? But for temporary adjustment you did it, so that's why. So I can say still it's a problem, right? So you are facing problems while deleting the data. Let's say somehow finally you adjusted Venu and you requested Venu to watch this area. Okay, so it's not a good solution, but we follow it at this moment. Now we'll see one more problem, that is updation anomaly. So far we have seen insertion anomalies, deletion anomalies. Now we'll see updation anomaly. What is updation anomaly is, so Raju's wife name is actually Rani. So he want to change this wife name to Maharani. So just name change, that's it. Okay, he's not changing his wife. Then so we have to write Maharani. Okay, M Rani, M for Maha. Then there is a problem. What is the problem, sir? Since Raju Rani data is repeated in multiple places, while doing updation, there is a chance that you update here Raju and Maharani, but in the second tuple, if you don't update, then you face a problem. So you end up with inconsistency. That is called updation anomaly. When data is repeated in multiple places, there is a chance that you update in one place and you don't update in another place. That is called updation anomaly. When there is a repetition of data, usually it occurs. So how to avoid that? We have to avoid the repetition of data. Here see, unnecessarily you are repeating this information that Raju's wife Maharani, Raju's wife Maharani. Imagine the situation where you are not repeating this information that Raju's wife is Maharani two times. Then if there is only one place we have this data, then only in this place I update and I don't face any problem. That's why updation anomaly can be solved only if there is no repetition of data. But how to avoid the repetition of data? So given combination of table, in this one definitely I get repetition of data. Example, there is a new area called 4. Let's say something is, this one is, let's say some small ABC and 5000 square meters. See this data. And one Mr. Raju want to watch this area. So 1 comma Raju and wife is now Maharani, right? See, you are repeating the data, though you don't want, but here in this combination of data, we have to repeat it. So without repetition, we can't write an entry for 1 and area ID 4, correct? So when Raju watches multiple areas, then multiple times we have to repeat that Raju's wife is Maharani, Maharani. If you miss it, then you get inconsistency. That is called updation anomaly. So far we have seen 3 anomalies: insertion, deletion, updation. But how to solve this problem? That is normalization. So Mr. Cod and Boyce, these people proposed some rules. Okay, that set of rules if you follow, automatically all these anomalies can be solved: insertion anomaly, deletion anomaly, updation anomaly. So I can say that normalization is nothing but imposing some systematic rules on your table so that your table doesn't have this design problems, otherwise these anomalies. That is a major concept of normalization. For that, what to do? What are the rules? So there are 4 normal forms usually, like, which are popular: first normal form, then second normal form, then third normal form, then BCNF. So we study that normal forms and we'll try to understand what is the concept of each normal form, why so many normal forms. So after that we will see the 4th normal form. So what is that 4th normal form? All these things one by one. Okay. So to understand all these normal forms, first you should understand a concept called functional dependency. What is functional dependency? I will tell you. Let's see functional dependencies. So what is functional dependency? I explain first informally. After that, I will explain you formally. So example, this is your table. Some employees, and every employee should have exactly one car. We'll see how to ensure that later. So assume that in my table, every employee should have exactly one car, and that car name should decide the parking area. These are the rules, let's say, I want to impose on the table. So you remember from now onwards, whenever we store the data in our tables, then only data is not important. So the relation among the attributes also important. Example of such relation is, here car name should decide the parking area. Consider this company. So let's say this company name is XYZ. This company has one weird rule that, so car name should decide the parking area. There are 3 parking areas for them. A is one area, parking area, which is AC parking area. B is non-AC but little bit spacious. C for congested. That means that parking area is very congested and it is highly risky to park the cars in that area. Just for connecting these functional dependencies to our discussion, I am explaining this concept. Now, example in that company, so nano car should go to, because they are small in size, they have to go to always parking area C. So that is the strong rule they have. Now bench car, let's say, it should go to the best parking area, which is nothing but AC parking area. Now there is one more car, BMW, let's say, that BMW car should go to parking area B. In that way they have rule. Okay. Now from now onwards, once they have this rule, then we'll see somehow DBMS ensures it. How it ensures, we will see. But before that, we will see, let's say somehow DBMS is maintaining this rule. That means if a new user comes, that new employee comes into the company with a car nano, then if he enters this data into the table, what happens we'll see, nano comma C. That's okay. But if mistakenly this fellow employee ID 4, if he keeps that car in parking area B, then what happens you see, because nano always should go to parking area C, that is the company rule, then here nano is going to parking area B, which is mistake here, correct? So somehow DBMS can find out this mistake. We will see later that, but at this moment this is a mistake. To say that this is mistake, so we have to develop some theory, right? Why it is mistake? The thing is, car name always should determine the parking area. That means nano car always should go to parking area C. That means whenever here nano and here nano, this corresponding entry should be always same first of all. Let's say later, because initially I fixed it to C, then this also should be C, then only it is correct? So this concept is called functional dependency. What is functional dependency is here, car name determines parking area. Whenever you repeat the car name, then parking area also should be repeated. Example, nano. So first time you enter the data nano comma C correctly, let's say in the table. Second time if someone enters data nano, then the parking area must be C. Third time one more person enters a nano car, then the parking area must be C. So to ensure this condition in practicality, so DBMS will take care of that. Yes, we can somehow instruct DBMS to do that, but in theory what we say is this is called functional dependency. Okay, so finally there is a functional dependency between car name and parking area. So formally speaking, we write like this from now onwards. Whenever there is this kind of relation, that means A determines B. So here we say A attribute determines B attribute, or A functionally determines B. Otherwise B is dependent on A. All are same. So that means that whenever there are two tuples T1 comma T2, I am formally defining now. So there are two tuples T1 comma T2 in the table. If T1 of A agrees with T2 of A, see here, tuple number 1, tuple number 2. If tuple 1's, tuple 2's values agree, then the corresponding parking areas also should agree. So how to write it is like this. If tuple 1 of A equal to tuple 2 of A, then what should happen is tuple 1 of B should be equal to tuple 2 of B. If you ensure that, we say that you are ensuring or enforcing functional dependency A to B. Understand? Example here, car name determines parking area. Whether it is correct or not, we will see. Example, if I make this one C, then you are ensuring this functional dependency. What is it? Car name determines parking area. So why? We'll check. Whenever car name, let's see these two tuples. Tuple number 1, this one, and this is tuple number 2. Okay, so just apply the rule. Tuple 1 of A, this is A, this is B. Car name determines parking area. So tuple 1 of A equal to tuple 2 of A. Correct or not? Tuple 1 of A nano equal to tuple 2 of A. What is tuple 2? Here nano, right? So nano equal to nano, then tuple 1 of B must be equal to tuple 2 of B. Correct or not? So in the B we have C here in tuple 1, in tuple 2 of B, in tuple number 2 B, this is the B column equal to C. If you ensure that, we say that you are ensuring functional dependency. Sir, how to violate functional dependency? Simple. So try to take two same values at car name, that means nano, and make parking area here something B. Then this rule will be violated. So check it out. Tuple 1 of A and tuple 2 of A both are nano here, but tuple 1 of B, which is C, tuple 2 of B is B, correct? C equal to B is false. So you violated the functional dependency, right? So this is the concept of functional dependency. Let me summarize it. Whenever you say a attribute, otherwise set of attributes. First of all, we started with single attribute, but we can extend it to multiple attributes also. Let's start with single attribute first. Example, some single attribute determines another single attribute. Then what should happen is, for in the entire table, any two tuples agree on A attribute, the same tuple should agree on B attribute. That's it. So we'll see one numerical example now. Now we'll see this example. In this example, we'll see that functional dependency concept. Example, my claim is in this table, especially for this instance, A is determining B. A determines B, whether it is correct or not, we'll see. Really A determines B, whatever the two tuples you take, if A values agree, I am not saying that A value should agree. Try to understand. I am saying that if A values agree, B value should agree. Okay, it's implication. So we'll see that. Let me take two tuples here. So whenever, sir, I have two tuples, A values are not agreeing, then no problem. But if A values agree, then B value should agree. So simple. That's why what you do is take the example tuples where A values agree. So that's why let me take this as tuple 1, this as tuple 2. You see now. A values agree, correct? Really A determines B, then the corresponding B values you should see, they should agree. Yes, they are agreeing. But it should happen for every two tuples, not only for a particular tuple. Don't say like this, sir, I checked T1 and T2, these two, that's it. I don't check other tuples. Then you are not doing correctly. According to the definition of functional dependency, for every two tuples, if tuple 1 of A equal to tuple 2 of A, then tuple 1 of B should be equal to tuple 2 of B. That's it. Now let me take these two as two tuples, right? Tuple 1, tuple 2. Now see here they are agreeing, then B values are not agreeing, correct? That's why A determines B is definitely wrong for this data, right? Similarly, can we see some students argue like this, sir, you see here 2 and 3, they are not agreeing. See, if they don't agree here, no problem. If they agree here, then here also they should agree. So again some students argue like this, sir, they are not agreeing here, but here they are agreeing. Example, they show this kind of data and they say, sir, there is a mistake. What is that? Tuple 1 of A and tuple 2 of A are not agreeing. Yes, okay, they are not agreeing. But tuple 1 of B and tuple 2 of B are agreeing. Yes, it can happen. The only thing which cannot happen is when tuple 1 of A, see, remember one thing, if tuple 1 of A, this is a rule, equal to tuple 2 of A, then only talk about tuple 1 of B and tuple 2 of B. So definitely tuple 1 of B equal to tuple 2 of B. Remember one thing, whenever this is false, then still we can say that the rule is satisfied. That's why your example, if you see tuple 1 of A, this is T1, let's say this is T2. Tuple 1 of A is 2, tuple 2 of A 3, 2 equal to 3, false, right? Then in logic, false implies anything is true. That's why you don't need to check this one. Irrespective of that, your rule is satisfied. So I say that from now onwards, this is the rule. To violate this rule, tuple 1 of A and tuple 2 of A should be true. That means equal. And these two should be unequal. That means this premise should be true and conclusion should be false. I want this kind of example to prove that A determines B is false. Okay, but I can show that. So how to violate this rule? Here I can violate, you see. Tuple 1, this is tuple 2, right? So tuple 1 of A, 2. Tuple 2 of A, 2. 2 equal to 2, yes. But tuple 1 of B, which is 3, and tuple 2 of B, 4. 3 equal to 4 is false. That's it. So that's why finally A determines B is absolutely false. The rule is violated. Now we'll see another example. Let's try B to C. Is this true? Let's try all possible combinations. We know one thing, really this rule is violated. The only possibility, tuple 1 and tuple 2 of B should agree first of all. Only such cases we should examine. Now here I can examine, you see, these two equal, then the corresponding C also equal. So fine, satisfied. Now these two equal, then the corresponding values are not equal, you see. 4 and 4 equal, B determines C is absolutely wrong because B values are agreeing but C values corresponding, I'm talking about, are not agreeing, correct? So that's why here it is a mistake. Now at least we try A, B determines C. Is it true? Sir, how you check two attributes at a time? The rule is like this. Tuple 1 of, whenever you want to say that the combination of attributes AB determines C, then this should happen. Tuple 1 at AB combination, let me extend the concept. Tuple 1 of AB equal to tuple 2 of AB, then what should happen? Always tuple 1 of C equal to tuple 2 of C. This is a rule. Let's try that. So take every AB combination, but they should agree first of all. If they agree here, they don't disagree, they don't agree at C, then that is the mistake. So tuple 1 of AB, you see, 1, 2 combination. Here 1 2 combination, right? So tuple 1 of AB is 1 comma 2, right? I take like this. Now tuple 2 of AB, so I'm taking these two. That is also 1 comma 2. They agree. Then C value should agree. Yes, they are agreeing, correct? 3 equal to 3. Now is there anywhere they are agreeing? See, 1 2 1 2. Other than that, they are not at all agreeing anywhere. Some students argue that, sir, here they are agreeing, you see. This is tuple 1, this is tuple 2. No, the combination of AB should agree. Here the combination is 2 3. Here the combination is 2 4. They are not same. So what happens if you take that as two tuples? Then they will be 2 3 and second one 2 4. 2 3 equal to 2 4. No, false. False implies anything true, so rule is not violated. To violate the rule, premise, this is called premise, the premise should be true and conclusion should be false. Understand? So finally I can say that AB determines C is correct here. Correct? Now one more question, you check yourself whether C determines B. I don't know. Let's check it out. C determines B. Now we came to a position where we can understand functional dependencies clearly. Now let's try to understand what is the formal definition of X determines Y. We write like this, X implies Y. That means X functionally determines Y. Otherwise Y is dependent on X. Otherwise Y is determined by X. Everything is same. Okay. Now for every two tuples in the table, if tuple 1 of x equal to tuple 2 of x, then tuple 1 of y should be equal to tuple 2 of y. Then we say x determines y. So informally I say like this, when x values agree, y values which are corresponding should agree, that's it. Now sir, who will decide that? How do I know that really my attribute set x determines y or not? How I can decide? Generally for that you should be domain expert. That means you should know about that domain which you are talking about. Example, this is one of the domain, like this is student table. In this student table, so student ID is unique identification number to uniquely identify the student. Student names, we know that every student will have names and every student's father name is represented here, and marks. Now my question is, let's say you know about this data. Now you tell me, can I say student ID determines student name? Is it meaningful? Yes, it is meaningful, because we know that student ID is unique identifier, right? So you are not going to repeat that number for multiple students. If that is the case, whenever example, first of all we see the data. Let's say, what is the concept of x determines y? Really x determines y for every two tuples. If x value agree, then y value should agree, correct? Now here you see, for student ID really determines student name. Whenever, imagine that, let's say there are two tuples in the table where student ID is getting repeated. Don't ask me why, just imagine. So if really this student ID is repeated, then definitely student name, let's say one means Raju, then this one also is Raju, isn't it? That means whenever student ID gets repeated, then student name also getting repeated, correct? That means whenever student ID values agree, names also agree, right? That is the property of student ID here. Then such student ID determines student name. So this is perfectly right. Sir, yesterday I have seen some instance of the table, so where there is one more one in the table and her name is Rani. Then you are violating the def. That means you don't know about domain. Already we started the discussion with that student ID is unique for every student. If really that is case, then how can you write 1 comma Rani? You never write. In that scenario I am talking about, like otherwise anything can be violated, right? So you know that student ID never repeated for different people. Okay. So if that is the case, then definitely student ID determines student name. So by ensuring that the student ID primary key, we can do it. Already I told you, DBMS can definitely remember this rule, student ID determines student name. Simply make it unique so that you can't repeat it, so that no two people can take the same number. That's why we can ensure this kind of dependencies, also known as integrity constraints. So using integrity constraint concept, we can imitate, otherwise we can enforce this rule, functional dependency. Understand? So there are some other rules, like example, father name determines marks. If you have such rule in the table, I'm not saying that that is correct, but what if really there is a weird rule, father name determines marks for particular table, then we can take the help of DBMS. In DBMS we have a concept called check and assertion. Okay, using the assertions, by writing the assertions, we can say that, my dear DBMS, I am writing an assertion. That assertion is nothing but such a way that father name should decide marks. In that way we can write the assertions and we can ensure. So we don't talk about that. Okay, leave it. So that's the implementation part. We try to understand the theory, what is actually functional dependency. Okay, so remember that yes, we can write assertions such a way that all these FDs or functional dependencies can be enforced if you want, not a problem. But the question is how to identify them. So it is easy for me because I know this domain, student names, everything. I know about student IDs. Definitely student ID should determine student name. And if you have a data like this, then that is not the proper data, correct? So I can say that in this theory, student ID determines student name. Now, is it true that in your table, student name determines marks at any time? Is it true? We'll see. Really student name determines marks. Then whenever student name, example Raju, whenever Raju is repeated, marks has to be repeated. Example, first Raju's marks are 25, second Raju's marks also 25. Is it necessary? Need not be, correct. So I'm just talking about, see, user can write wrong data. I'm not saying that. Is it theoretically correct or not? You tell me. According to your data properties, like is it legal data for you? That means always Raju means 25. Is it true? No. There can be two Rajus. Example, this Raju is from Hyderabad and another Raju from Mumbai. Okay. Then there can be multiple people with name Raju. Their marks might be different. So now student name determines marks is absolutely false because names are agreeing but marks are not agreeing. That is what the the meaning of this data, right? That is the way this data is defined, right? So for such data, student name determines marks is absolutely wrong. So who is deciding everything? Subject expert. The subject here is students. So if you know about students, you decide the rules. Otherwise, someone who knows about this data will decide the rules. As a database designer, let's say you are the designer, you are going to apply the normalization process. For that, let's say you don't really need to know the rules like what is the functional dependency in the table. Okay, don't worry. If you don't know, also be happy. Who will give the rules is the database expert, otherwise domain expert of this data. He will tell you all the rules like student ID determines student name, everything. Once we have such rules, then we start normalization. Okay, so now we try to understand such functional dependencies. First of all, let's say you are subject expert, then you tell me, so can I say that student name determines marks? Absolutely false. Can I say father name determines marks? Absolutely false, because when father name is repeated, then marks need not be repeated. Example, father name, because father name, let's say Raju's father is something, imagine some X. So there is another Raju, when there is another Raju, that Raju's father name might be something, let's say this Raju's father name also same. Now see this situation. Raju and Raju, there are two Rajus, their father names are same X. In this situation, marks can be different like this 25, 26. Now father names are same. It doesn't mean that the person is same. Then if there are two different people, they can have different marks. That's why father name cannot determine marks. This is an example. Okay. Now see this situation. In the real world, there can be two students with same father name. Student number 1, student number 2, and father names are same X and X. Then marks might be different, right? Because they are different students, so marks might be different. Now see, this is tuple 1, this is tuple 2, this is father name, this is marks. Then in these two tuples, father names are matching but marks are not matching. Yes, there is a possibility, right? So that's why in theory we say that father name does not determine marks. And one more important point I will tell you, that is, some people see the data and decide everything. So by seeing the data, you should not decide. It's a property of attribute rather than the values of otherwise instance. Example, what people argue is they do like this. They say that, see sir, student ID and father name, let's say marks. They take this table. I'm just showing only important data, and they say like this: sir, in my table there are two students, 1 comma 2, father name let's say X and here also X, and both are having marks same. See sir, now can I say that father name determines marks? Don't say that. At particular instance, in this snapshot or photo, it appears that father names equal but marks also equal. It doesn't mean that every time it happens, right? Tomorrow, so there might be this kind of data. It's obvious that one more person might come and his father name also same like X, but he may get different marks like 26. So what I want to say is, by seeing the instance, this is called instance. Instance is nothing but a particular snapshot of the table, like at this moment what is the data you have, that is called instance. So by seeing this instance, I can't say that father name determines marks, otherwise father name does not determine marks, anything. Don't decide. So how to decide? Only by understanding the property of father name and property of marks rather than values. Okay, so that's why I never see the values and decide everything. I see the properties. So we know that student ID's property is unique identifier. Student ID determines father name, student ID determines marks. But father name in the theory, that means we know the property of father name. So father names may be same, but they may be different people. That is the property of father names, and you might have different marks. It is possible. Correct? That's why. So by seeing the data, don't decide. But definitely I can say that without seeing the data, I can say that father names cannot determine marks, right? It's easy to understand. So finally, for other tables, for this table you can understand, but for long tables, otherwise some unknown tables, like you don't know data, what is the meaning of every attribute, for that you don't require to decide whether functional dependency holds or not. Okay, here example, student ID determines father name, right? That holds. But for new tables like which you don't know, like what are the attributes, everything, for that is not your responsibility. There will be one subject expert or domain expert who will decide, whoever created that table, whoever wants it, they know everything about the properties of attributes. They will give you the rules, otherwise indirectly or somehow they explain you the rules. Okay, now let's slowly develop the theory about functional dependencies. First of all, we start with axioms. Axioms are nothing but some blind rules. Okay, so every functional dependency satisfies these blind rules: reflexive property, augmentation property, transitive property. So they are called universal rules. Okay, so we'll see one by one. So there will not be any proof for this reflexive property, but it is very obvious to understand. First of all, let me state what is reflexive property. If x superset are equal to y, then we say x determines y. Example, x is nothing but, from now onwards whenever I take this kind of capital letters, they are set of attributes in the table. Example, I have a table with 4 attributes a, b, c, d. For simplicity, let me take x as some set of attributes a comma b comma c. Fine. Then tell me one set of attributes y which is superset or equal to, subset or equal to x. Let's take some subset of x which is b comma c. Now whenever you take x superset or equal to y, then this property says that x determines y. We see whether it is correct or not. From now onwards, either I write x as a comma b comma c, otherwise I can take x as abc. There is no difference. If I take abc, otherwise a comma b comma c, my intention is some set of attributes abc. That's it. Now this rule says that x means abc, right? Abc determines bc. That is what the rule. Since y contains x, correct, then why abc determines bc is obvious. We will see what is the meaning of functional dependency. We know that in your table, this is, let's say, your table. In this table, any two tuples you take, tuple 1 tuple 2, if abc values agree, that is the rule. You know that, right? Example, what is the rule of x determines y? If x determines y means whenever x values agree in two tuples, y value should agree. That is the functional dependency rule. So here also, if abc values agree, let's take abc here. If abc values agree on two tuples, Let's take first tuple's values a1, b1, c1, and second tuple's values should be a1, b1, c1, then only they agree, correct? Now this rule says that whenever abc values agree, then bc values agree. Is it correct or not? That's obvious, because in abc we have bc. If really to agree abc values, a value should agree, b value should agree, c value should agree. See, a value should agree, b value should agree, c value should agree. Then automatically bc combination also will agree, right? See here, b1 c1, b1 c1. Finally, tuple 1's abc equal to tuple 2's abc, then automatically tuple 1's bc equal to tuple 2's bc. That is quite obvious. That is called reflexive property. From now onwards, you have two sets x comma y. If y contains x, otherwise x is superset or equal to y, then automatically x determines y. Okay, so example this one. So here finally abc is one x here, y is bc, then abc determines bc. The reason is quite obvious. When abc values agree, further definitely bc value should agree on that rows, correct? That's quite obvious. That's why I say these are all axioms. So I can't give theorem or proof easily, but I can just state them and I can explain them with intuition, right? So let's remember it as a blind rule. Okay, now see the augmentation property. What is augmentation property? We will see. Let's say there is some set of attributes w determines z, and set of attributes x determines y. Then wx determines yz. Whether it is correct or not, we will see. For that, I take, for simplicity, let me take w as a single attribute and z as single attribute, x as single attribute, y as single attribute. Later we can extend it to set of attributes. So if w attribute determines z, x attribute determines y, automatically wx determines yz. Why it is correct, I can prove. So let's say really this property is wrong. What should happen? This wx determines yz should be false, but these two rules should be correct. Remember one thing, whenever we have a rule with if condition, if something then something, then what we have to prove is to prove that this is wrong. Really your intention is to prove this is wrong. Premises should be true, conclusion should be false. That means these two rules should be true, remember, but conclusion wx determines yz is false. Let's say really it happens, then this rule is wrong. Let's assume that this rule is wrong, then wx determines yz should be wrong. Let's focus on that wx yz attributes in the table. There are a lot of tuples. I don't show them because it's time waste. So otherwise, what I do is I take the structure. I assume that there are a lot of tuples in this table wx yz, and there might be other attributes also. I don't bother about them. I bother about only wx yz. That's why I'm showing only wx yz. Now what is the question? We have to prove that wx determines yz is false. How to violate this rule? Already I told you. Really you want to say that wx determines yz is false. Wx, there should be definitely two tuples. At least. There can be infinite tuples, but at least two tuples you should show where wx values should agree, yz value should not agree. Okay, let's really wx values agree, then it will be like this: w1 x1, here also w1 x1. Really in two tuples wx values agree, this will happen. Then at the same time yz values should not agree. Tell me one example where yz value should not agree. If y values won't agree, then yz values will not agree, correct? Let's take an example such a way that this is y1, this is y2, but this is, let's say, z1, z1. So I am only focusing on y. I am just ensuring that y values are not agreeing. But we know that already w determines z, x determines y. Already x values are agreeing, correct? Such a way you planned. If really x values agree, then y values also should agree. Why? Then only x determines y is correct. Really x determines y is correct. This will become y1. Sir, I am sorry, actually this is an example, sir. Some student is arguing like this. He is saying that now you see, sir, wx values are agreeing, but yz values are not agreeing. Before that, these premises should be true. What are they? W should determine z, x should determine y. Really w is determining z. Check it out. w1, w1, if they are equal, these two also should be equal. But no, right? So they are not equal. For that we have to make it equal. Why? Then only w determines z. Why W should determine Z? Don't ask me, because that is the starting point. The rule says that if W determines Z, then when W values agree, Z values agree. When X determines Y, when X values agree, Y values agree, then automatically really WX combinations agree, then YZ combinations will agree. That is augmentation rule. Now we proved, right? So this is augmentation property. Now we'll see transitive property. Transitive property is easy to explain. And one more thing, don't say that, sir, it is obvious in the world. Every time transitive property is correct. No. For every mathematical system, transitive property is not correct. Okay, only few times. So this transitive property might hold. So, but fortunately for our functional dependencies, transitive property holds good. You take any functional dependencies, transitive property holds good. Why, we will see. The rule is like this: X determines Y and Y determines Z. Though I did not write here if, it means my intention is if. If X determines Y and Y determines Z, then X determines Z. Why it is true, sir? Let's say I am wrong. If I am wrong, then X determines Z should be false. This is the only way we can make X determine Z false. Let's try. X here, Y here, Z here. For simplicity, I assume that X and Y and Z are single attributes, but you can extend it to multiple attributes also. So X, Y, Z are, let's say, single attributes, and you want to say that X determines Z is false. For that, what should happen? In the world, you should show at least two tuples T1, T2. On that, X value should agree, Z value should disagree. Then only X determines Z will become false. Really it is false, let's say. Then it should be Z1, it should be Z2. But before that, we know that X determines Y, Y determines Z. Don't violate them. If really X determines Y, if X1, I'm sorry, here it is X1. Yeah, so X1, X values agree, then Y value should agree. No doubt on that. Then only X determines Y. Really Y determines Z. See here, if Y values agree, then Z value should agree. But why did you write two different values here? It's your mistake, right? So it should be Z1. Initially, I thought of violating X determines Z rule, but I was not able to do that because X determines Y, Y determines Z are already given. If whenever these two rules are true, then automatically X also determines Z. That's quite obvious. Just now we proved. Let's try to prove it in different way. Let's take X determines Y and Y determines Z and ensure it. From now onwards, whatever the two tuples you have, X should determine Y. That is what given. Really X determines Y, then X values agree, then Y value should agree. Remember it. Now, really Y determines Z. Whenever Y values agree in any two tuples, then Z values also should agree. Then automatically, if X values agree, Y values will agree. If Y values agree, then Z values agree. Automatically, X determines Z. If X values agree, automatically Y values are agreeing. Y values agree, then according to this rule, Z values also agreeing. Indirectly, Z values are agreeing. So that means X automatically determines Z. These three are the fundamental rules we should remember. Let's summarize. One is reflexive property, second one augmentation property, third one transitive property. Whenever X is superset or equal to Y, from now onwards, X, we say that always X determines Y. Second one, if W determines Z, X determines Y. Whenever you see, simply say that WX determines YZ. Third one is, if X determines Y, Y determines Z, then X determines Z. That is a transitive property. Now we have two more important properties. One is union rule and decomposition rule. They are not fundamental rules. They can be derived using these three rules. Let's see that. Okay. Now we'll see the two rules, union rule and decomposition rule. In union rule, if X determines Y and X determines Z, then that X determines YZ together. That's quite obvious, but I prove it using these fundamental rules. So we know that X determines Y and X determines Z according to augmentation rule. See augmentation rule. W determines Z, X determines Y, then WX together determines YZ. Here also I apply that. W, this one is Z, this is X, this is Y. WX, that means XX determines YZ. What's the meaning of XX? Is it X square? It's not multiplication, right? So it is nothing but taking all the attributes of X and all the attributes of X. So finally we have to do union here, right? Union is appropriate. So XX means X union X, which is nothing but X. Finally, I can say that X determines YZ. Understand? So we got it. This decomposition rule. X determines YZ, then we have to prove that X determines Y and X determines Z. Since it is AND operator, both should be true, correct? Let's prove one by one. First of all, my target is X determines Y. I prove it. So really X determines YZ, then we can say that YZ also determines Y. This is obvious. So this is also known as trivial rule. What is trivial rule is? So that is easy to understand. Like any rule, otherwise any functional dependency which is implied because of reflexive rule is called trivial property or trivial rule. So this is trivial dependency. So that's obvious. When y and z values in a row agree in two rows, automatically the corresponding y values agree. That's obvious, right? So that is called trivial property or trivial rule. So in functional dependencies, this is trivial dependency. Remember blindly from now onwards, trivial dependency is a dependency which is implied. Otherwise, we can which one can be proved using reflexive property. So here there is a reflexive property. Yz superset are equal to y. That's why yz determines y. Correct? So remember it. This is universal fact according to reflexive property. In the problem, it is given that x determines yz. So if I combine these two, so x determines yz, yz determines y. According to transitive property, x to y, y to z, then x to z. If x to yz and yz to y, then automatically x to y. In that way, we can prove this one. Now let's take the second one. So x determines z is my target. For that, what I do is, first of all, I prove that yz determines z because of reflexive property. That is obvious. So yz superset are equal to z, hence yz determines z. So x already determines yz in our problem, right? So that is already given. Then x to yz, yz to z, then x to z, transitive property. So this is also proved. Finally, from now onwards, when x determines set of attributes y and set of attributes z, then I can say that x determines set of attributes y and x determines set of attributes z. Quite obvious. So these are all 5 important axioms. You should remember them. So we are going to use this axiom so many times to understand normalization concept. Okay.